This is AP Calculus AB. We are on our notes for 11-5, Advanced Volumes of Revolution. This is the very last new lesson for AP Calculus AB in this curriculum. Our objective today is to find the volume of solids generated by rotating an area around different horizontal axes today. So instead of just the x-axis, it's a bunch of different axes. We're assuming that we're still rotating around horizontal, although you can rotate around vertical in more advanced cases than this. So before I said that axes could be extended into the third dimension by rotating around the x-axis. Now I'm going to say it's rotate around any axis, not just the x-axis. Again, I'm going to be using that same link that I used from 11-4. So this was the exact same sequence of pictures that we had in 11-4 where we rotate around the x-axis. We start with some base area, and this is in the 3D viewer. Once I have that area and it travels through space, it goes through space and it creates our 3D area. It keeps going through the space and finishes, and you get this type of cone that has this center right here that is open. You can see the center of that cone is open. It's a little bit harder to see over here, especially on a black and white printer. However, notice what happens if you do two different types of lines. What if instead of rotating around the x-axis, I rotate around this line y equals 1, where it's a little bit higher? If the line is closer to the shape, then the shape actually rotates less, and by the end of the shape, it rotates, and you can see that that circle looks to be a lot smaller than that circle, so the volume is smaller than the rotation around the x-axis. However, if I rotate around a line that is farther away from the x-axis than it originally was, right? It used to be right here, and now it's a little bit farther away, then you can see that that shape is even larger than the original shape. So what is some way that we can take into account the fact that we might be rotating around different axes to make our volume bigger or smaller? Again, everything comes from a slice. So for this diagram right here, I'm going to be comparing two different slices, and it's roughly the same x-coordinates, but I'm going to be comparing these two final pieces. So let's go ahead and do our best attempt to draw the slice. So the slice is going to come up and around, and then we have a dashed line that comes out behind this slice right here, which I'm going to say that slice right there I'm going to compare to this slice right here. So this slice right here, and we'll go ahead and shade that one in as well. What's happening with each of these two slices? So, and if you can't really see that rotation, you can think of it as I guess I didn't do the annotation over here. You should try practicing this as well. If I'm rotating this correctly, I should have a line that comes out like this, and then some line that comes in and then closer out, and you can say, okay, it rotates around that axis, rotates around that axis. I'm really talking about this thin piece of slice that's right there, or if I'm rotating up here, it's going to be more of a reflection like this and out like that. And then we have our 3D shape, and again, we're talking about this thin slice within that shape. So how do you do that down here? You can see that the bigger one is first. So this bigger one is the first cross section, and this smaller one is that second cross section. It's really hard to see that it does have a hole in the center. You can kind of see that hole when it's first starting to rotate right here, but there's a bigger hole and then it's a smaller hole. But the key thing here is that the area, this area, is exactly the same in all three scenarios. So therefore, this area that it passes through and sweeps through 3D space is the same as this area that passes through 3D space. These two distances are the same distance. So just like before, we're going to go ahead and draw some axes out from the center. Let's go ahead and assume for both of these that I have some sort of center point, and we're going to say, okay, the distance to get from here to here is going to be the distance to get to the most outside object. We'll say that that distance right here, we'll do a curly brace. That distance here is going to be some sort of function like f of x, but really I'm going to just call it the outer shape, because when I'm rotating around an axis, there's not really a top or a bottom. We could use f of x and g of x notation. I'm just going to say that this one was the top, and this one, well, not the, I just said not to do that. Ugh. I just said we're going to say this is the outer shape, and we're going to do the inner shape. And in this lesson, you'll see that that can be confusing. So again, I'm going to be comparing the outer shape to the inner shape. And just to give you a preview of what's to come, what if I rotate, instead of a line that's down here, what if I rotate by a line up here, then this one becomes the outer and this one becomes the inner. They switch, right? So coming down here, we're going to say that this one is the outer function. So we'll say outer function. And we're going to represent that one with a capital R. That was a terrible R, though. Let's make that a little bit better. And then we're going to say that this distance from here to here, this distance there, is going to be the inner function, which we're going to represent with a lowercase r. And just to remind you, I could have chosen any slice that I wanted. I could have done a really tiny circle, a really big circle. The fact that this is represented by a function means I can do any slice that I want. It could have been small, it could have been big. This is just one example, and since this is a function, it could be anything, right? All right, so again, this is still represented by two shapes. We have our red circle, which is going to be about that size, and then we are going to subtract our smaller inside circle, which I don't want an ellipse. I want a circle. I can't even draw a circle very well. There goes a circle, right about that size. And again, if I'm annotating each of these, this circle, if I come from the center out, this is going to be capital R. This circle over here is going to be lowercase r. So as a review, this was going to be pi r squared for our area, and this one over here is going to be pi little r squared for the area, and then I just subtract those two. And normally what happens here is you factor out the pi, and you can say this is really pi times the quantity of this capital R squared minus this lowercase r squared. So there's minus here with these two things being squared, and eventually you slap on an integral symbol here, and then it becomes the integral of, usually I put the pi on the outside. It can be on the inside or the outside, doesn't really matter. And this is going to be capital R and lowercase r. Both of these are going to be squared with a minus sign. That's generally the formula. Over here, it's going to be a little bit different now. So in order to get this new length, we're going to say this length right here, that used to be capital R, but we had to make it smaller, right? So if we really have to compare it to the diagram up here. It used to be, and I think maybe looking at this original picture is probably the easiest way to see it. I used to be saying this distance from here to here. That used to be the entire function. But now what I'm doing is I'm moving that and making it a smaller radius by this factor. We're saying that this is the equation y is equal to k, just to make it any general number. I know I said it's y equal to 1. I just made up some positive number, but really this is y equals k, so I can move this line up or down. So I want to say that this k value is the thing, this distance between, I guess I should say, between here and here, that distance right here is the distance that I'm subtracting. So I'm subtracting this k. So down over here, I'm going to say this is really capital R minus the k value that I was talking about. And then in order to get this blue distance here, and you can already guess where I'm going to go, this distance right here is going to be that lowercase r, and again, minus k. So the formula becomes a little bit more complicated, but again, it's the same thing. We're going to go through the whole thing again. This is going to be, the red circle is now slightly smaller, and the blue circle is even smaller than it was before. It's going to think I'm drawing an ellipse because I'm terrible at drawing circles. There we go. So we're going to say that that distance from here to here is going to be capital R minus k, and the distance from here to here is going to be lowercase r, and then we have to do minus k for each of these, minus k for each of them. And then we're going to do our areas. This is going to be pi r squared, so pi, and then this entire distance right here, this entire distance is the radius. So this entire thing gets squared. So we're going to say this entire capital R minus k, that entire thing gets squared, and then I have to subtract this entire circle, and that entire circle is another pi r squared. Pi, this is going to be our radius there squared, and the radius here is going to be an r minus k. Okay, and then again, you can factor out the pi's, and then you can say that this is going to be really pi times, and I think it might be faster for me to just copy paste these things. So pi times this thing, paste, and then I can put a giant square bracket here, minus, and then I just have to copy this thing as well. Let's grab all of you and say copy, paste, minus all of that, and then finish the square bracket because we factored out that pi. And then finally, to get our formula, we're going to just put the integral on all of this. So all of this stuff, we're going to copy and paste, and we're just going to slap an integral symbol on here. We're going to say it's the integral of all this. The integral of all of this. Again, all of these bounds should be from the bounds from your area, from A to B. So we'll come over here and say the bounds are A to B. Where A to B, just as a reminder, if we come up to our area, we're going to say that this, I should say this is X, wait, this is the X-axis. This is A and this is B on our X-axis because it's the area bounds. So we're going to come down here and say we're going to put all that with a pi. And if I'm being super duper official, which I'm not going to do for ink, but I could put all of this in parentheses and write a dx here, but I'm not going to do that for this video. I'm just going to leave it as so. And then I can, again, convert the capital R is really my outer function and my lowercase r is my inner function, and I do get this formula right here. So it's maybe a long-winded explanation on how to get from our original formula from 11-4 into this one. Essentially, the old 11-4 formula, we didn't have any k, or k was 0 rather. So if I have k is equal to 0, you scribble out that term, you scribble out that term, and that formula should look very familiar to you because that is last lesson's formula. All right, so let's see one example of this and we'll call it done for the notes. So in example 1, we have our same equation as last time, but instead of rotating around the x-axis, now I'm rotating around the line y is equal to 2. My advice to all of you is to draw that line. Even if it's going to be like off the graph and you can't see it down there, whatever, still draw it because it will help you determine which is your outer function and which is your inner function. So if I draw the line y equals 2, it is going to be a horizontal line going through 2, which means I really have a horizontal line that goes right through here. And again, it's a little bit off, so I'll go ahead and move you to right there. And remind yourself, I am rotating around that line y is equal to 2. So that means it's pretty clear that my outer function is actually going to be the bottom this time, and my inner function is going to be the top this time. And then I'm just using that same formula that I've memorized, which is, don't forget your pi. I always will forget my pi. We'll see if I can remember that in the worksheet. It's going to be the correct bounds, which is going to be from A to, okay, I forget what this bound is over here that we had from last time, but it's this x coordinate, which is a little bit off. I'm going to move that to the right spot right there. So the question is, what is the x coordinate? Again, here's how you find it. This is a calculator enabled question right here. So let's go ahead and use our calculator. So let's move you over. Calculator, we need you. Where is our calculator? There it is. Move you to the left since I'm right-handed. And here we go. So we're going to say y is equal to, we need 2 sine of x. And then our next function is 2 to the power of x minus 1. Make sure all of x minus 1 is in that power, which it is for me, minus a half, or you can say minus 0.5, that's fine too. And then I'm going to change my window to be the same window as my graph here, which is from 0 to about 2.5-ish. So I'm going to say from 0 to about 2.5, 2.5. I'm going to be lazy and do a zoom 0, and it should automatically fit this thing. And there it is. So to find the intersection, I'm going to hit second trace to do a calculation of an intersection. So I do option 5, and just follow your prompts. I think my prompts are different. So I'm going to hit 2. My right bound is 2.5. And I found my intersection just like the last video. Same answer. I get 2. Whoa, I want to draw this with not dash line though. 2.133. So we have our bounds, then I come back here and I'm going to say, okay, I'm not going to do from A, I'm going to go from 0 to 2.133, and then I'm going to do my first function, my outer function first. So my outer function is actually g. Now, I'm not going to write that whole function like I did last time. I'm just going to say g of x, that entire function, minus the value that I'm talking about. I'm rotating around 2 here, and be careful here. I'm not going to do an example down here because I want to make this video as short as possible, but if you had a negative number, you'll have a double negative happen and you'll actually be adding. In this case, I don't have a double negative, so I don't have to worry about it. So I'm going to do minus 2 and that entire thing, quantity squared, then minus my inner function. So my inner function I've already labeled. My inner function is f of x. So I'm going to come over here and say that my inner function is f of x. I'm going to subtract 2 yet again, and then I'm going to square this thing. And if I want to be super technically correct, I can say all of this thing in parentheses, in square brackets, I guess, because I ran out of parentheses, dx. I like to alternate my parentheses with my square brackets so it's clear to see where the beginning and ending is. Again, that pi could have been on the inside, it could have been on the outside. It doesn't really matter where the pi goes as long as it's being distributed into each of these terms. So typically speaking, if I had no calculator enabled, if this somehow were say no calculator, it would tell me to write but do not evaluate, and I would be done right now. But because this is a calculator enabled question, I need to actually type that in and get the right answer. So I'm going to hit second mode to quit out of this, and then I'm going to type in what I see there. So it's going to be second pi, and then I'm going to do math 9. Okay, my bounds are going to be 0 to 2.133. And then I'm going to come over here. I want to be careful about my parentheses. So I'm going to start my parentheses for my g of x minus 2. And then at the end of this parentheses, I'm going to square this. So my g of x is my y2, I believe. Yes, so g of x is my y2. So I'm going to hit second mode to get out of this. So I'm going to type in alpha trace to come up get y2. So y2 minus my 2. And then I'm going to end my parentheses and take that to the power of 2. And then minus, start the next set of parentheses because this is going to be squared as well. I'm going to write f of x, which is my alpha trace y1. And then I'm also going to subtract 2. I'm going to end my parentheses, and this is going to be to the power of 2. Now everything is entered correctly. I just hit enter, and I get my answer, which is going to be different than our last video. And I get 9.335, rounding automatically to 3 decimal places because that's how I have my calculator settings. Excellent. That concludes our notes for 11-5, Advanced Volumes of Revolution for AP Calculus AB. And that concludes our last new lesson of AP Calculus AB. Thanks for watching.